All right, so in this video, we are going to do the entire curve sketching algorithm for this rational function over here. The first thing we note is that we can actually factor this, the denominator over here, by difference of squares, just x plus 5, x minus 5, and this is going to help a bit. So now we can start answering some of the basic things in the question, like let's start with the x-intercept. For the x-intercept, it's just the solution to the numerator over here, which in this case is just 0. And then for the y-intercept, I'm just going to sub in my x's as a 0. So 2 times 0 is 0. 0 divided by negative 25 is also 0. So our x and y-intercept are both 0. And typically, if you get one, you'll get the other. Next, we can do vertical asymptotes. Vertical asymptotes are just the denominator, the solutions to the denominator. So in this case, it's x equals to positive 5 and x equals to negative 5. And the last thing we can do is the horizontal asymptote. And since the degree on the top is larger than the degree on the bottom, degree is 1, degree is 2, your degree on the top is smaller than the degree on the bottom, your horizontal asymptote is always y equals 0. So now we can get into deriving the function. I'm going to derive the function over here using my quotient rule. And I'll always derive from the unfactored form. It's always easier. So let's do quotient rule here. F equals to 2x, g equals x squared minus 25, f prime equals to 2, and g prime equals to 2x. And now I'll sub it in my quotient rule. So f prime times g minus g prime times f divided by g squared. I can simplify my numerator over here. So this is just going to be 2x squared minus 50 plus 4x squared, and the denominator stays the same, x squared minus 25 squared. I'll combine like terms in the top. So 2x squared, oops, this is not a plus, this is a minus. 2x squared minus 4x squared is negative 2x squared minus 50 over x squared minus 25 squared. And now I want to make this equal to 0 to see if I can find any critical points. This is my derived equation over here, my simplified derived equation. So let me replace the y prime with a 0 to see if I can factor this. The denominator will automatically disappear because it will multiply with 0. So I'm just left with this. And then this is basically going to be impossible to solve. As you can tell, x squared equals to 25. You cannot square root a negative number. So there are no critical points. Since there are no critical points, the only things that will go on our number line are the vertical asymptotes. Usually it's vertical asymptotes and critical points, but since there are no critical points here, we're only going to put our vertical asymptotes on a number line and find our intervals of increase and decrease. I'll start by subbing in a point over here into the derived equation. Now the bottom is always positive, so I can just look at the sign of the top and it will automatically tell me the sign of the entire equation because the bottom is always positive. It's not going to affect our solution at all. So let me sub in negative 6 into this equation. And I get a negative value, which means that my equation is decreasing over here. Let me sub in a value in between over here. So I'll just sub in 0. If I sub in 0, I'll get a negative value again, which means this whole range is decreasing as well. And let me sub in a value higher than this over here. Let me sub in positive 6. And I get a negative value as well. So all three ranges are decreasing. So my intervals of increase, well, I have none. There are no intervals of increase. And my intervals of decrease are from negative infinity to negative 5, negative 5 to positive 5, and positive phi to positive infinity. So I have 3 intervals of decrease for this function. Okay, now that I've completed this over here, I'm going to go to my second derivation. I'm going to derive this function again to find my inflection points. And again, I'm going to use quotient rule over here. So f equals negative 2x squared minus 50 and g equals to x squared minus 25 squared. F prime is negative 4x. G prime equals to 2x squared minus 25 times 2x, which is just 4x times x squared minus 25. Okay, now I gotta do my y double prime using my quotient rule. So negative 4x times x squared minus 25 squared. F prime g minus g prime 4x x squared minus 25. F is negative 2x squared minus 50. And this is all divided by g squared. So that's x squared minus 25. And there's a square here. If I square that again, the new exponent is 4. I want to simplify this a bit now. So I'm going to divide all 3 terms by x squared minus 25. So this cancels. This becomes a 1. This becomes a 3. So this is the equation a bit simplified over here. And now I want to expand and combine like terms in the top. So that's going to be negative 4x cubed plus 100x plus 8x cubed plus 200x. Denominator stays the same. Can combine like terms in the top. So I'll get 4x cubed plus 300x divided by x squared minus 25 cubed. Again, common factor out probably a 4x here. I think 300 divided by 4 is 75, but I'll double check that. Yep, it is. So this is my most derived equation, I guess. I factored a bit here, so this was also my y double prime. That one's fine as well to use. Actually, this one's probably better. But now I want to make it equal to 0 and solve. So denominator is just going to disappear. And for the numerator, this is going to have a solution of x equals to 0. This one is going to have no solution because x squared plus a number never has a solution. So I have an inflection point at 0, comma. If I summon 0 back into the original equation, I'll get it to be 0, 0, which is the same as the x and y intercept. So I have an inflection point at 0, 0 as well. Next thing I want to do is I want to find my intervals of concave up and concave down. So on my number line, I will put my inflection point, and I'll also put my vertical asymptotes as well, because on your second number line, you have your vertical asymptotes and your inflection points. So I'll start by subbing in negative 6 into this equation over here. And actually, I'll do this one here. Because the bottom is cubed, you have to put it into the whole equation to get an accurate solution. You just cannot put it into the top. You got to make sure to sub it in the top and the bottom. So I'll start by subbing in negative 6. One's a bit of a bigger formula, so it might take some time. Negative 6 squared minus 25 to the power of 3. And I get a negative answer here, so this is concave down. Next, I'll sub in a value between these two. So I'll sub in a negative 1. And if I sub in negative 1, I'll get a positive value. It's a very small decimal value, 0.02, but it is still positive. So this is going to be concave up. Now sub in positive 1 over here. Get a negative value again. So this is concave down. And last, I'll sub in positive 6. And I'm assuming this is going to give me a concave up value. And I will check it in the calculator. And that is right. I get a positive value. So this is concave up. So let's do my intervals of concave up and concave down. My intervals of concave up are from -5 to 0 and from 5 till infinity. And my intervals of concave down are from -infinity to -5 and 0 to positive 5. So 2 intervals of concave up, 2 intervals of concave down. And the last thing I need to do is I need to sketch out my function with all this key information. So I'll do that over here. So when you do your sketch, the first thing you always want to do is you want to put your vertical asymptotes. X equals 5. X equals to -5. Here's my X and Y intercept at 0, 0. And it's also an inflection point as well. Now, what else do I have? I know that the function is decreasing as I go from left to right. And I know that there's also a horizontal asymptote at Y equals to 0. So let's say I'm starting on the left here. I have two choices. I can go like this upwards or like this downwards. Since the function is decreasing and concave down, it means I have to go downwards like this. There's no other choice of decreasing and concave down. So that's that end of the function right there. Now from -5 till 0, the function is still decreasing. The function is actually decreasing the whole time. If the function is decreasing from here to here, it has to start at the top. It can't start at the bottom because then it's going to be increasing. So it has to start at the top. It has to go through the inflection point, and then it's going to switch to concave down as well, but it's still decreasing the whole time over here. So this is what the middle over here looks like. And as we go to the end, it's again decreasing. So it has to start at the top. It's also concave up. And it's going to turn sideways here at a horizontal asymptote. So this is the final graph of this function.